Let's work through an example where we compute the integral of a scalar function over a surface embedded in R3. The surface that we're working with is M, which is the portion of the cylinder x squared plus y squared equals 9, in which the x coordinates are at least 0 and the z coordinates are in between -1 and 1. So we get the half of the cylinder that lies where x is greater than or equal to 0. So that's shown here, where we've cut off z at 1 and at -1. The function is f of x, y, z equals x squared y plus z squared. All right, and so we want to compute this integral of f over m ds. So it's a surface integral because we're integrating our function over this curved surface that's embedded in R3. In order to do this, we need a parameterization, and that's what's written out here. So we're going to rewrite our surface integral in terms of a double integral with respect to the coordinates u and v that are used in the parameterization. And so we plug the parameterization into f. Instead of x, y, z, it's r of u, v. And then we have to throw in this integration factor, the partial to respect to u of r cross the partial to respect to v of r. The magnitude of that vector is a scalar function of u and v, and we have to throw that in. So in this case, the parameterization r of u, v, well, the x and y coordinates must satisfy this relation, so we should probably just use the standard parameterization of the circle, which is 3 cosine u, 3 sine u. So that'll guarantee that x squared plus y squared equals 9, but now on the other hand there's still, so that solves the x and y coordinates, but then there's still the z coordinate which is independent of x and y, and there's really no relation that z satisfies, so we can just let z be equal to v. So it's just this independent third coordinate. Now the domain D of the parameterization, so the relevant values of u and v to exactly describe this surface, the set of points exactly once. So the u values are going to range from what to what? Well, u is this angular coordinate, and essentially I'm going to want -pi/2 to pi/2. So those are the angles that the x coordinates will be at least 0. And my v coordinates, well, v is just equal to z, and so it's from -1 to 1. Okay, so my domain for this parameterization is in fact a rectangle, so the bounds will all be constant, and that'll keep things fairly straightforward. Alright, so now we need to do a couple things. We need to know what this quantity is and what this quantity is. So let's compute the cross product first. So r sub u, well, we just compute. We get -3 sine u, 3 cosine u, and then v isn't a function of u, so we get 0. And then r sub v, well, neither of the first two coordinates are functions of v, so we're going to get 0, 0, and then 1. So then r sub u cross r sub v is what? So, I like to write these, one under another, so we can just think about the determinant method for computing the cross product. So the first coordinate of the cross product is the determinant of this 2 by 2 matrix. So we get 3 cosine u, and then the second coordinate is the cofactor with these 4 entries, and so we get -3 sine u minus 0, but then we have to take the opposite of that, so we get 3 times sine u. And then finally the third coordinate, because we're going to use the determinant of these 4 entries, but because these are both 0, we're going to get 0. Alright, so in the end, this r sub u cross r sub v is this vector 3 cosine u, 3 sine u, 0, which is very close to r. It's just instead of v, we have 0 for all the coordinates. And that actually makes sense because the normal vector, because this is a vertical cylinder, the normal vector should be horizontal. And that's exactly what we're finding right here is that r sub u cross r sub v has z coordinate equal to 0 everywhere. So I get these horizontal vectors that point straight out away from the cylinder, and that's what we're seeing in the first two coordinates there. Okay, so the magnitude of r sub u cross r sub v is simply going to be 3, which is fairly straightforward based on the fact that this coordinate is 0 and we have the basic trig functions here. Okay, so now we're ready to rewrite this integral. So we have the integral, so u goes from negative pi over 2 to pi over 2, and v goes from negative 1 to 1. Now f of r of uv means plug in these formulas for x, y, and z right here. So x equals 3 cosine u, so I get 9 cosine squared u, that's x squared, and then times y, which is times 3 sine u. And then plus z squared is going to be plus v squared dv du, but I can't forget to multiply by the magnitude of r sub u cross r sub v, so that gives me a factor of 3. Okay, and so now we've rewritten our surface integral using the parameterization in terms of this double integral, and so now we just have to do the work of computing the double integral. Okay, so the first term when I integrate with respect to v, it's constant with respect to v, so I'm just going to get the length of this interval, which is 2. So I have 9 times 3 is 27, times 3 is 81, and then times 2 is 162, and then the integral negative pi over 2 to pi over 2 of cosine squared u sine u, and then plus, and then here this is constant with respect to u, so I'm going to get the length of this interval times the integral of v squared with respect to v. So the length of the interval is pi, so I get 3 pi times and then v cubed over 3 evaluated from negative 1 to 1. Okay, so taking a look at this integral, what do we have? So if I do a substitution for cosine u, then I'm going to have then the derivative is negative sine u du, which is close. I'm just off by a minus sign. So in the end I get 162 cosine cubed u evaluated from pi over 2 to negative pi over 2, which accounts for the minus sign. And then I get plus, and then when I plug in, so these 3's cancel out. When I plug in 1, I get 1, and when I plug in negative 1, I get negative 1, so the difference is 2, so I get plus 2 pi. Okay, now on the other hand, when I plug in plus or minus pi over 2, cosine goes to 0, so this whole term goes to 0. So in the end, I'm left with simply 2 pi. Alright, so we have evaluated this surface integral. Again, we accomplished this by coming up with a parameterization of my surface and then using this method to rewrite the surface integral in terms of a double integral, and then simply just a matter of some brute force calculation to come up with the answer 2 pi.